So now we're going to move into section 11.2, which is inference about two means for dependent samples. And it's a little strange to do 11.2 before we've done 11.1, but that's because 11.2 is actually kind of the simplest of the hypothesis test that we're going to learn in chapter 11. It's very similar, extremely similar to one that we already learned in chapter 10. So let's see that. So first thing we're going to do is remind you about independent versus dependent sampling. So when individuals selected for one sample do not dictate or have a relationship with the individuals in the second sample, that's independent sampling. Dependent sampling, often called matched pairs samples, is when the individuals selected to be in one sample are used to determine the individuals in the second sample. So it's possible also to match against yourself. That's actually pretty common, where you'll do like a pre-test and a post-test, or they'll have you I don't know, do something with your right hand, then do something with your left hand. That's you paired up against yourself. Or husbands and wives, brothers and sisters, twins. Those are all dependent sampling, right? Because the first person affects the second person, right? They're interconnected. Independent sampling is when it's two independent groups. Generally, you only measure them one time. So like I have a whole batch of one group over here and a whole batch of another group over here, and they have nothing to do with each other, and I'm going to measure them once. Right? Dependent samples tend to be one group that you measure twice. So you do the husbands, then you do the wives. You do the pre-test, then you do the post-test. You have them sip Pepsi, and then you have them sip Coke. Right? Those are dependent samples. All right, so first thing we're going to do is decide whether the sampling method here is independent or dependent. Then we're going to determine whether the response variable is qualitative or quantitative. The reason we want to know about that is because qualitative response variables are proportions. Those, what percentage of people are going to vote yes, what percentage of people are going to vote no. Yes and no are qualitative things. Quantitative things are things that we're going to be either using the mean or standard deviation to measure. So what's the center, what's the spread, that kind of thing. Average body temperature, average score, average, these are quantitative measures. All right, so the accuracy of verbal responses is tested in an experiment in which individuals report their heights verbally and then they are measured. So you go to a person, you say, what height are you? They tell you, and then you measure them and see how it compares to what they actually were. Data consists of the stated height and the measured height for each individual. All right. All right, so let's see here. What kind is that? Is it two separate groups measured once, or is it one group of people measured twice? Well, it's rather obvious, but it's a dependent sample. You are measuring one group twice. You're measuring them verbally, and then you're measuring them physically, right? So you're asking them what height they are. Height is a quantitative variable. It's actually a continuous quantitative variable, to be honest with you. So it's height, right, is measured in inches. It's measured, so that is totally a quantitative thing that you're trying to measure about these people. And it's a dependent sample because, if you're 5'7", you're not going to say, I'm 7 feet tall. You're going to say you're 5 foot something, right? Somewhere around there. So it's you being measured twice, being measured once by words and once by actions. All right, now what about the next one? Oopsie. There we go. The U.S. Census Bureau publishes information on the ages of married couples. Suppose we want to determine in the U.S. the mean age of married men differs from the mean age of their wives. Okay, so you're going to get husbands and wives and figure out the ages of each. Well, that's a dependent sample again, and quite frankly, that's quantitative again. You're measuring people's age. It's technically a continuous variable, although we usually round it to the nearest year, which would make it discrete. Right? But the mean age is a quantitative. It's a number you're measuring about people, right? And it's dependent because husbands and wives have a relationship, right? You're not getting random men and random women. That would be independent. But you're getting people that are connected together. So that is definitely dependent. All right. So now we are going to run a hypothesis test on some matched pairs data. We have a study that was carried out to determine whether, I'm sorry if I say this wrong, Reiki touch therapy was useful in the reduction of mean pain level in chronic pain sufferers, including cancer patients. The pain level reported by a random sample of 13 patients before and after Reiki touch therapy is shown in the table. We are going to use the results to determine whether there was a reduction in pain after the Reiki touch therapy. Okay, so you have some pain sufferers, right? You're going to do this Reiki touch therapy and then see whether it reduces their pain. So why is this a dependent sample? Right? It totally is, but let's see if we can see why. Actually, I'm going to take that back. It's one group of people, the pain sufferers, that's right, measured twice, right? Before and after the Reiki therapy, which I have no idea what that is. Oops, there you go, I paused you. It's just a simple Google search found out that it's a Japanese massage technique. All right, now back we go. All right, so we're going to find the difference in the pain levels before and after. And now you can use your calculator. I'm going to show a calculator, Excel, all sorts of things, but you can use your calculator to totally do this very simply for yourself. So let me see if I can bring up a calculator. And actually, I'm going to make it a little bit smaller just so we can see here. All right, so stat, edit. Now, here are the 13 different patients. So we don't need those numbers. All they're doing is numbering off the patients for us. They could have done A, B, C, D, E just as easily. What matters to us is the before and after. This was their pain levels before for these 13 patients, and then this is their pain level after. So what we're going to do is we're going to go up and clear out the old. Sorry if that's small. Here, let me make this a little bit bigger. Okay. I guess I'll bring it back. And then I'm going to type in the numbers. So if you want to pause me and go look at the numbers, you can, but oopsie. Let me get in here. Where? 6. There we go. Getting there. Oh, I don't know why that happened. Hold on. There, my computer was possessed for a second. All right. Then 2, 3, 3, 4, 2, 5, 1. I think I got all that. And then I'm going to go to the right and enter the after. So it's 3, 1. And you want to make sure they line up, because if you've got one column that's longer than another, that means you did something wrong. But mine line up perfectly. 8 with 8, 4 with 4, 6 with 1, and so on. Now here's the beautiful thing. Now I know this particular data set was really kind of simple, so you could have done most of these in your head. I get that. But I want to show you a little trick. So if I go to L3 and I go up, it's going to ask me, what's L3 going to be equal to for you? And I wanted after minus before. You want to look in the problem, see if they give you a hint of which direction they want you to go. If not, it's up to you which way you want to go. You can choose before minus after or after minus before. It's kind of tomato, tomato, right? All right, so they want after minus before. So I'm going to do L2, that was my after. So second 2 minus second 1, that's L1, enter. And it figures all the numbers out for me. Look at that, right? Without me having to type all of it. Beautiful, huh? All right, so I know this one was kind of basic, but it's a nice little trick to be able to use, especially if you've got some pretty ugly data in there. Let's see, -2, -3, -3, 0. And if you just look at this, most of this is negative, so that means we probably are showing some effect, but we're going to have to prove it using statistics. Now the other way you can find those differences if you have Excel is you can say before is here, after is here. Let me type all these up. Hold on one sec. There they are, right there. So I've got them all typed up. And then I would just make the difference right here. I would say equals after, which is cell B2, minus before, which was cell B1. Enter. Then we go back to that cell and drag it down. And there you go. It figured out all the numbers as well, right there. All right, awesome. Okay, so we've got all the differences, and now we want to find D bar and SD. Now you may be thinking, what the heck is D bar? Well, you've seen X bar, right? X bar was the mean for your data set. So D bar is your sample mean of your D for differences, right? So this is finding the mean of the differences, and this is finding the standard deviation of the differences. So let me write that out. Mean of differences. And then this one is the standard deviation of differences. That's what you're finding. Now, we've known how to find those values for quite some time. So if you're with Excel, you would just type, so let me type it down here, mean and S. So, or if you like D bar and S sub D, right? So that's what these are. So D bar is equal to the average of these data, and SD would be equal to standard deviation dot S, because this is a sample of these data. And there we go. So there are the two values right there. Now if you have a calculator, let me grab the calculator, you would go to Stat, Calculate, one variable, and our list is L3 this time, so you want to hit list second 3, L3. We're leaving frequency list blank because this is not a weighted mean. Go down to Calculate and press Enter. And there's the same numbers we got from the Excel. Negative 1.923 right there, and 1.605. Remember, because it's S. This is a sample, not a population. All right, so let me grab these numbers. This was negative 1.923, and this was 1.605, roughly. I mean, we're rounding a little bit, but you get the general idea. All right. So now we get to move on to the actual hypothesis test part. So the hypothesis test for matched pairs, t-test, should look very similar to a lot of the other hypothesis tests we've done. Namely, first of all, you're going to need a simple random sample. It's going to be matched pairs to do this. So you've got to look for your data set, see if it's matched pairs. The differences are either normally distributed with no outliers or your sample size is larger than 30. And notice I would give right up here, for those of you with a calculator, it's a t-test that you're doing on the calculator. All right, so we're going to determine our null and alternative hypotheses. And this time, instead of mu, we're talking about mu d, the mean of the differences. D stands for difference. Alpha is the same as it was before in chapter 10. T0 is now d bar over SD over the square root of n, which is very similar to what it was in section 10.3 for regular t-tests. N minus 1 degrees of freedom, and so on. You have your classical approach versus your p-value approach. Right? So pick which test you're doing, and that helps you draw your picture. And then you're going to compare your critical values with the test statistic if you're running the classical method, or if you're using the p-value method, you're going to compare your p-value with alpha and write your conclusion. All right, so on the next page I have the instructions, but I'm about to show you a lot of those instructions anyway. So, but notice I show both methods here in the instructions. The raw data method, which is what we're going to use right here because we have the raw data. Or if I gave you the statistics instead, you would run it this way. All right, so let's see. We won't have time to finish all of this, but we can probably do the first bit, which is suppose we want to conduct a test whether there has been a mean reduction in pain level after the Reiki therapy using a 0.05 level of significance. Keeping in mind that we found the differences as after minus before, how should we put our hypotheses? All right, so let's see here. We want the mu for after to be less than the mu for before, right? Oh, I'm going to make that bigger. All right, so now suppose I subtract mu before from both sides, because we did after minus before, right? So I'm going to subtract mu before from both sides. Oops. There we go. Now what's going to happen over here is that they're going to cancel, right? Mu before, take away mu before, makes big fat 0. So you're going to have mu after minus mu before, oops, there we go, minus mu before, less than 0. All right, but mu after minus mu before is how we defined mu d. So we're going to say mu d is less than 0. There's our hypotheses right there. So that's the alternative, I should say. So this is H1 that we're really concerned about, because right, why don't I care about the H sub 0? Well, because H sub 0 always has equality for our course. So we're not really concerned about that so much. All right, so there's the alternative hypotheses. So our hypotheses should be, let me make this up. Hold on. There we go. They should be that. And this is over here is the explanation for why. So it should be mu d equals 0 and mu d less than 0.